example, we will use the McCabe Thiele method to solve a binary distillation problem. The question says that a mixture of 44% benzene and 56% toluene needs to be separated into a product of at least 98% benzene and one of at least 98% toluene. It has been suggested by the plant engineer that this could be achieved using a distillation column at 1 atmosphere with a reflux ratio twice the minimum reflux ratio and a saturated liquid feed. We need to know how many stages are needed in the distillation column. It is helpful to pick out the key information. First, we need to find out which is the light key component. To do this, find the boiling points of benzene and toluene. We get 80.1 and 110.8. Therefore, the light key is benzene as it has a lower boiling point. The mass fraction of benzene in the feed is XF, which is equal to 0.44. The mass fraction of benzene in the distillate XD is 0.98. We know this because benzene is the light key component and therefore will leave through the top of the column, and it should leave at 98% purity. The mass fraction of benzene in the bottoms, XB, is 0.02. We know this because the heavy key component, toluene, leaves the bottoms at 98% purity. The rest must be benzene. We're told that the actual reflux ratio is double the minimum reflux ratio, therefore R equals 2R min. The feed is a saturated liquid, therefore Q equals 1. The process occurs at 1 atmosphere pressure, so VLE data at 1 atm should be used. This is shown in the table. Now we can start solving the question graphically. Start by labelling the axes x and y and drawing the line x equals y, which will be used as a reference. Also plot the data given in the table to form a vapor-liquid equilibrium curve. Next, we need to draw the feed condition line. Start by plotting the line x equals xf from 0.44 on the x-axis up to the line y equals x. This ends at the point xf. Next, look at the equation for the feed condition line. The feed condition line has a gradient of q over q minus 1. We're given that q equals 1. Therefore, the gradient is 1 over 0, which is infinite. The line is going to be a vertical line. From the feed point, draw a line straight up to the VLE curve. Next, we need to plot the distillate condition. Start by plotting the line x equals xd, starting from the point 0.98 on the x-axis and drawing up to the line y equals x. Then draw a line from the point xd through the point of intersection between the feed condition line and the VLE. Make this line go up to the y-axis. This is the operating line for the minimum reflux ratio. Next, we need to calculate the minimum reflux ratio. We do this using the line we just drew. Use the general equation for the operating line. This tells us that the y-axis intercept value is equal to xd over r min plus 1. This is because the line we drew is at the minimum reflux ratio. Rearranging this gives r min equals xd over the intercept minus 1. Reading off the y-axis, the intercept is found to be at 0.3874. Therefore, the minimum reflux ratio is 1.53. We need to draw the actual operating line for the rectifying section. The rectifying section is the section between the feed and the distillate. To do this, first calculate the actual reflux ratio. This is double the minimum reflux ratio and is equal to 3.06. Use the general equation for the operating line. Substitute the value for the new reflux ratio to find the value for the new y-axis intercept. This is at y equals 0.2414. Draw a line connecting this point to the point xd. Then redraw the feed line back to the operating line. Next, we need to draw the operating line for the stripping section. This section is between the feed and the bottom product, so the line will be plotted between xf and xb. Start by plotting x equals xb by drawing from 0.02 on the x-axis up to the line y equals x. This ends at the point xb. Draw the stripping section operating line from the point xb to the intersection of the feed line and the rectifying section operating line. This is the general equation for the stripping section operating line. The y-axis intercept is highlighted. Next, we're going to draw the equilibrium stages in the rectifying section. We do this by stepping off. Start at the feed point, which is the intersection of the operating lines and the feed line. Draw a line vertically up to the VLE. Then draw a line horizontally across the operating line. Repeat this to the end of the operating line. Each step represents an equilibrium stage. Now draw the stripping section equilibrium stages. Start from the same point as before and repeat the process. Each step represents an equilibrium stage in the stripping section. Add up the steps to find the total number of stages in the column. The first step in the bottom left-hand corner represents the reboiler. We can sketch the column to illustrate this. The first 6 stages make up the stripping section. Then we have the feed. The rest of the stages are in the rectifying section. Finally, add a condenser. Therefore, to separate benzene and toluene at the required purity, we need 13 stages.